Okay, so my name is Aoife and I'm a first year PhD student at the Institute of Astronomy, and I'm really interested in looking at the relationship between the black hole and the host galaxy mass of galaxies and seeing how they evolve and how they interact. And I do this with a technique called gravitational lensing, and I think on your screen you'll be able to see a lovely example of gravitational lensing. So here we have we have a central massive galaxy. It could be a cluster, and behind it, directly behind it, really far away, is another fainter galaxy, which the light from that faint galaxy is being bent into a ring, so we can see it as this lovely ring known as an Einstein ring. And this is really useful because we're able to see really distant galaxies like this, because this gravitational lensing also magnifies the image as well, so I study those. So yeah, looking forward to your questions, and yeah.
Yeah, I think I was just muted when I gave the introduction. So just by the way, in case you notice some problems with the audio, just let us know in chat. We have a lawnmower and stuff going on, so we are working on that. Otherwise, yeah, welcome to the 8th episode of Astronomer, in case I didn't say it before. And for those of you who don't know it yet, we are here for 1 hour and answer all your questions about astronomy, science, etc. You can just write them in the YouTube chat or on slido.com. There's a link in the YouTube description. Or on the Periscope chat or Facebook chat. And just ask us anything. And while we're at it, we already got one question from a few hours ago. Now you can start with that one on Slido. What's the difference between an asteroid and a planet? Because they orbit the sun and they're rocky. So yeah, how do you differentiate between what makes a planet as opposed to an asteroid?
I think this is quite an interesting question, because we have to think about a lot of things, and definitely I remember, I say a few years ago, it's from many years ago now, back in 2006, when we were trying to decide whether Pluto would be a dwarf planet or a planet, and there was a lot of people wanted Pluto to be a planet, and sadly it's no longer a planet, it's something called a dwarf planet. But we could also apply this to asteroids, where there's 3 conditions for a planet to be a planet. 1, it's spherical. 2, it orbits the sun, which Pluto does it and the Earth does it and all the other planets. But also number 3 is it has to clear its own orbit. So with Pluto, it orbits in something called the Kuiper belt, which is with loads of other asteroids and rocky things, and they orbit the sun together, whereas the planets, they all orbit and there's nothing in the way of them going around the sun. So kind of the main difference between that is that the asteroids would orbit in the asteroid belt or the Kuiper belt, along with Pluto and many other things. So yeah, that's the difference. And these tend to be a lot smaller than planets. Asteroids, they're maybe a couple of kilometers across. So tiny in comparison to the Earth.
Yeah, so Pluto lost its planet status, but maybe one day we'll find another planet. We'll see. There's some people searching for 9th planet again. We got another question that's about well, the kind of horizon until where we can see. So I mean, we can only see a certain distance in the universe, because what we think is that the speed of light is kind of finite. And the question is if this could be not because kind of the or that this could be because there's kind of an outer edge of the universe, like the oldest part where there are no longer any stars, and maybe if there could be anything different behind than the normal universe, like a lot of black holes that kind of pull the universe out, what could cause the expansion instead of what we currently think the expansion causes.
This is a really interesting question. I don't know, Stefan, what do you think?
Yeah, so I think that's really cool. So I mean, for the one thing, of course, it kind of is in a certain way true that the further away you look, the older the part gets. So actually, if you look in the universe and you look further than, let's say, like a few gigaparsec, so such that the kind of the age of the universe where you look at is less than a few 100 million years, there actually were no stars, because stars didn't have formed yet. So the further out you look, the universe indeed changes, but it's kind of the same universe, you just look at a different time. And when you think about it, like the expansion of the universe and what it could cause, so our current idea is there was a Big Bang in the beginning of the universe, and kind of everything started flying apart, and it's still flying apart. That's kind of the expansion. So it's just well, flying. There's also dark energy, but let's not talk about this now. And this makes the universe expand. So the idea here was, okay, let's suppose behind kind of where we can't see in the universe, so kind of behind our horizon, there could be lots of black holes pulling the universe apart. But you could detect this because if you had black holes kind of outside of the visible universe and they would pull everything apart, the pull would be stronger towards the kind of edge of the universe. While if the universe is expanding like from the Big Bang, it's expanding at the same speed everywhere. And we indeed do observe that everything is expanding at the same speed everywhere. So this black hole theory sadly doesn't work out. And it's probably the easier theory that there was just a Big Bang and everything's expanding now. We already got a few questions on YouTube. Does the axis of the moon precess like that of the Earth? Oh, I don't know anything about the solar system. Do you know, Eva?
Oh, I'm not sure.
So I think
actually not sure.
So the moon is tidal locked with the Earth, right? So that means the moon orbits the Earth so that it always faces the same direction. It would be interesting if if the Earth precesses if the moon. I suppose it does precess, right? Otherwise, we would see different areas of the moon, kind of in winter versus summer. So
yeah,
the kind of the plane.
We always see this.
Yeah, so I think that
we always see the same. Oh, sorry.
That's when you talk remotely. Yeah, we always see the same phase of the moon. So if the rotation plane of the moon would be different from the kind of plane in what the Earth rotates, you would kind of see the moon wobble. It might be wobbling. I'm not sure. I would have to look up some observations. Yeah, but if it wobbles, then it's not in our plane. If it doesn't wobble, it is moving exactly like with the Earth. We got two more questions. What's a wormhole and how does a galaxy work? Do you want one of those?
So, I mean, I can talk about the galaxy, or
there you
I can
go.
talk about the wormhole.
Then you can start with the galaxy.
Okay, so a galaxy is just a big clump of stars, lots of stars, and they all orbit, they all rotate around a common center of mass. So say you had a ball on a string and you swung that ball on that string and it's going around in sort of that circle as it's kind of orbiting that central point. And a lot of people think that central point is the black hole, but it's not. It just so happens that the black hole is at the center of the galaxy and they're all orbiting the sort of common center of mass. So these are just big groups of stars, lots of little sort of star clusters, and they're just orbiting around together. So yeah, they're just lots of stars going around together.
Yeah, and I think so that's also kind of interesting to see, if you look in the universe, you see loads of stars all over the place, but they're actually all inside our galaxy. Actually, all the stars that you can see in the night sky with your own eyes are only in a really small patch of the Milky Way. It's I'm not sure of the distance, but it's a few hundred or a thousand or so light years. So actually we can only see a really small part of the Milky Way, plus a few galaxies like Andromeda. And also stars only form within galaxies. So to form a star, you need lots of mass, etc. And you probably know better than me, but you have you have these kind of big amounts of gas you only have in big clumps in the universe, which form galaxies. So actually it's kind of the other way around. First you have big clumps of gas, and then in each of those clumps of gas you form a galaxy. And yeah, they have different phases of evolution, but I have no idea about those, so I can't talk about those.
I mean, if you look, say, at pictures from Hubble, you can see, we can even look in our picture here. So we've got our central lensing galaxy, this big yellow object, and these tend to be big galaxies, these big, what we call elliptical galaxies. And you can see they're kind of yellowy and red color, and this means that they have lots of what we call old stellar populations. So these have lots of old stars. Whereas if we can see our ring, our gravitational lens ring, our Einstein ring, and this is bluer. And this indicates that there are a lot of young stars, and this is actually a star-forming galaxy. So galaxies are currently, stars are currently being formed in this galaxy. So your young big stars tend to be blue, whereas your older stars and long-lived stars tend to be more yellow, red colors. So we can definitely see there's difference in the stellar populations here. So yeah, they go through different phases. Yeah. And these star-forming galaxies tend to be spirally kind of galaxies, whereas these yellowy elliptical galaxies tend to be sort of blobs.
Yeah, I think we got...
Not as exciting. We've got loads of questions.
Yeah, we got lots of questions now. Okay, so let me just go on quickly on the wormhole question. So it is there's kind of a mathematical possibility that space-time is kind of curved, so it doesn't necessarily have to be really flat. And it does get curved by objects like the sun and the Earth, and could also be not only kind of curved in one point, but it could also be kind of globally curved, like a sphere or something. And in addition to those simple shapes, it could also be folded in some way. And in these folds, then there could be kind of connections between 2 points of space-time that are really far away, but that could be connected to some kind of wormhole where there would be some kind of connection. But it's quite speculative, and we didn't find any kind of evidence for any kind of wormhole. So probably it will probably be some time until we find wormholes, if there are any at all. We already got a gravitational lensing question. So how does gravitational lensing help us to see the furthest objects in the universe?
So a gravitational lens, so this central galaxy, yellowy galaxy here, the central blob on the image, that tends to act as a magnifying glass. So just like we'd use a magnifying glass here on Earth to have a look at maybe words that might be too faint for us to see or too small for us to see, gravitational lensing basically, it just acts like a big magnifying glass, and then it will magnify the background galaxies a lot. And especially when we've got telescopes that maybe you can only see the brightest objects, because not all our technology is really advanced, but it's not so advanced that we can see everything. So we'll be able to see fainter objects, and we'll be able to see more distant objects as well. And it's quite a useful tool, and it's free, right? We don't have to spend lots of money to look for gravitational lenses. So that's another benefit.
How much larger does it make, or how much brighter does it make an image if you have a gravitational lens? Kind of.
It depends. It actually depends. So I have one object that magnifies it by a factor of 30. So it's 30 times brighter than the original image. And I've got some that are a factor of 3 or 4. So it just depends. It depends on how massive as well our galaxy is, our lensing galaxy, so our big elliptical galaxy or our cluster.
So if you have a bigger lens, of course, you can get a bigger effect.
Mm-hmm.
What would happen if there was no gravity in Earth for a day? Oh, that sounds like a question for the XCD thing. What if? I suppose there will be catastrophic consequences. So first, I think one problem would be all the oceans. Oh, actually, a big problem would be, I guess, all the air or the atmosphere kind of flying away. And I'm not sure how much of Earth's atmosphere will lose. Probably a lot. Given that Earth is kind of racing through space, and there might be I'm not sure how much the solar wind will strip away our atmosphere, but it won't be nice. Also, our oceans will have a problem because the water isn't kept anymore where it's supposed to be, and it will fly away. And of course, all the animals and humans will have problems, so not a good idea.
What's going to happen to the moon? Because the moon is gravitationally bound to the Earth.
Oh, yeah. Also, the moon's going to fly somewhere.
Or just swing off somewhere.
Yeah, and also the ISS, that's not so nice. It will fly away, I guess.
Yeah, those poor astronauts.
Please don't press that gravity off button, yes?
Yes, please, guys, we don't want that.
Can you explain a bit more about how gravitational lensing works? So which part of the original galaxy is which part of the ring?
So what you can see here, so this, when you get gravitationally lensed, so this ring is called an Einstein ring. So this is when we have our lens and we have our background, galaxy, and the background galaxy is directly behind the lensing galaxy. It's directly behind our orange blob. And what we're seeing here is we're actually seeing all of the galaxy. It's just being stretched out into an arc. Sometimes this could be 2 images. So we could see here that you can possibly see on the top left and right the images of the sort of big, Stefan's kind of highlighting those. These look almost identical, so these could be the same parts of the galaxy. It's just a double image, so it's just 2 images of the same galaxy that are lensed. It's particularly useful when we're looking at sort of what we call quasars, so these are active galaxies, and all we're seeing is the light black hole, or the accretion disk around the black hole, and these will be in points. So rather than seeing a lovely sort of Einstein ring, you'd see like dots. You'd have 1 dot here, maybe 1 dot here, or dots here, or you'd have 4 dots, also called an Einstein cross. So you're actually seeing the entire galaxy, and you're seeing multiple images of the entire galaxy.
So the light can pass both through the one way and the other way. And is there a big time difference between the 2 ways? So does the light from the one part arrive earlier than the other part?
So we can measure something we call time delays, and this is used for constraining a lot of parameters, cosmological parameters. So one of the images might have a little change in them because something's happened to the galaxy, and then a couple of days later, or 100 days, it's no more than a year, I don't think, being on the order of days, then you might see it in the other galaxy as well, in the other image of the same galaxy.
We got a question on Slido about black holes, so let's talk about this again.
Mm-hmm.
Do black holes die, and how many Earths go into the sun? Okay, so let's start with the black holes. Black holes, indeed, well, they have something that we call evaporate. So if you have a black hole, what can happen is they have this kind of event horizon, right? So there is like this. Let me open a picture of a black hole. I have a few here, I think. Actually, of course, always when I search a picture, I don't find it. So you have this event horizon. The black holes have this so-called event horizon where nothing can escape. And what can happen in the vacuum of space is that a bit of energy gets lost, and a antiparticle would get created and annihilate again. So they kind of get created, get destroyed, and nothing happens. But if you're close to a black hole, it could happen that one particle falls into the black hole, and the other one is kind of free and has nothing to do, and escapes. I mean, this is a very rough approximation, it's not completely correct, but it's kind of what you can imagine happening. And this means that everywhere where you have this this kind of horizon, there will be particles flying out of it. And that's also called Hawking radiation. And this leads to the black hole losing a little bit of energy over time. And this takes really long. So for a black hole that's kind of star size, it will take billions of years. I don't even know the number. It's really, really long. So it will take really, really long to die, but eventually it would indeed evaporate, and it would just kind of get smaller and smaller and smaller and disappear. For really, really tiny black holes, like if you had a black hole that's like the mass of, I don't know, an elementary particle, like a proton or so, or an atom, that would evaporate really, really quickly, like in the time of seconds, or much, much lower than seconds. So those would kind of die really fast. Aoife, do you want to say something about how many Earths go into the sun? Because I don't know the numbers.
Oh, I know how many. I think I know how many Jupiters go into the sun.
Well, let's start with Jupiters.
Jupiters, I think it's 1,000 or 10,000. You can fit 10,000, 1,000 Jupiters into the sun.
Let's say thousands of Jupiters and thousands of Earths go into the sun. But yeah, I would have to look up the exact number indeed. Oh, we also got a question about the Earth again. What if the Earth was half or twice the size? So I guess if that's actually an interesting question related to kind of how the what zone the Earth will orbit. So indeed, if it would be half the size, it would be also half the weight, and then it would have a different orbit around the sun. Or if it would be heavier, it would also move in distance to the sun, which would probably in both cases lead to the Earth no longer being in the so-called habitable zone. So the Earth would be so close or so far away from the sun, the temperature would be over 100 degrees Celsius or below 0 degrees. So water will either freeze or evaporate, and there would be no liquid water on Earth. And we don't think that we can have life without liquid water. At least we think that water is really good for life, and at the moment we don't have any idea how to create life without water. So that would also be a catastrophic consequence. Yeah, I think you're really treating Earth dangerously today.
Speaking of Earth, I've got the number of Earths you can fit into the sun.
Oh, okay.
It's about 1.3 million Earths you can fit into the sun.
Okay, so quite a lot of Earths. The sun is really big indeed. And we got loads of questions on YouTube, so let's go on with these.
Wow.
How do we determine the features of the original galaxy, say its shape, from the lensed image?
Okay, so this is actually a really complicated process. It's called, there's a whole area of science dedicated to this, and it's called lens modeling. So you can take the angles, if we can know the distance, we can measure the distance to our lensing galaxy, so our big orange blob there, and we can measure the angles at which light is deflected. So we use this by measuring the radius or the diameter of the Einstein ring as well. And we solve something called the lens equation, which I won't go into too much detail here because it's quite complicated. With computer models, we can then kind of build it back. We can build it back to what it was supposed to be, or its position where it is. So we can't know every single detail about it because there's a lot we don't know about how all of this works. But we can kind of get an idea of where this lensed galaxy, so the blue ring, was and what position it was. And also we can tell a lot about the features even just looking at the features in the ring, we can tell a lot about the galaxy, what it was doing, and we can be able to measure just about the distance to this distant galaxy as well.
Okay.
But it's a long, complicated process, and I need probably more than an hour to talk about it.
Okay, so let's not talk about this for an hour, but if you want to like know some more details, you can ask in the chat. And we got a question about what are stars made out of. That's actually an interesting question, and it depends a lot on how old the star is and how old the universe is when the star forms. So maybe I can start with the really early universe, because that's kind of my special area. Where kind of in the Big Bang, the universe like started with lots of protons and neutrons, and those turned into hydrogen and helium during the kind of during the Big Bang. So in the early universe, you only have hydrogen and helium, and all stars are made up. Well, I mean, the first stars can only be of helium and hydrogen because there's nothing else. So that's what they start to be. And then they start fusing hydrogen into helium. So first you get a bit more helium, and eventually they start fusing more, making bigger nuclei. So they start making carbon, oxygen, nitrogen, these kinds of elements. And eventually in supernovas, they explode and make all kinds of elements, essentially almost everything that you have in the periodic table. Eva, do you want to say a bit more about what kind of typical stars these days are made out of?
Okay, so what I would quite like about the universe is the universe recycles itself. So in these big supernova explosions, these will go off, and these will be lots of all these elements. And if there's, say, what we call like a stellar nursery nearby, so this is just lots of gas and dust together, it could influence star formation there. So kind of just make everything a little bit unstable in that dust cloud, so make some of these dust clouds more dense and some sort of less dense, and it could actually trigger star formation. And in these dust clouds would be these heavier elements. So these dust clouds will collapse down and start forming stars. So you tend to have a bit more of a mix. But with big stars, like Stefan said, they usually fuse hydrogen helium, and then it goes all the way up to iron. And there's a reason that it goes up to iron, because iron is the most stable element. And then beyond that, you need to put in energy to break them apart to create energy. So with fusion, you bash two things together and you get out energy. Whereas what we call fission, so this is everything after iron, you have to put energy in to then break them apart to get a little bit of energy, which is not, the universe doesn't like that. It's not so easy. You need that kind of energy in like supernova. So in stars like, say, our sun, these tend to be, they have a little bit more mixture of these things. So they have like a little metal, what we call metal content. So when we define metal in astronomy, we say everything that isn't hydrogen and helium is a metal.
Sorry about that.
They will have a little fraction of metals in them, but they are still mostly made up of hydrogen and helium. And then as they sort of reach towards the end of their lives, they'll start fusing more heavier elements. But yeah, hydrogen, helium, tiny bit of metal.
Yeah, the next question we got was about seeing black holes. So can we actually see black holes with our eyes or with telescopes? We cannot see them with our eyes because they are far too small, relatively speaking, and too far away to see them. But there are black holes in the center of our galaxy, and there's a really large black hole in the center of the galaxy M87. And what people actually did is take a lot of telescopes all over Earth and all use them kind of as one big telescope, so make an interferometer image. And if you combine lots of telescopes, you can look at structures that are as small as if you had a telescope that was actually as large as the longest distance. So if you had a telescope that was the size of Earth, you could indeed kind of see the black hole, or rather the shadow of the black hole, in M87 and in our own galaxy. And what you reach with just adding up a bunch of telescope, which people call the Event Horizon Telescope, sorry, that's a typo on the slide, you get kind of this image, so it's a bit blurred out, but you can see in the center, you have the kind of shadow, so no light is coming out of the black hole because no light can escape of a black hole. And actually you see kind of around, like the circle you see here is slightly larger than the black hole or than the event horizon itself, because light that goes just past the black hole also gets pulled in the black hole and doesn't reach us. And then what you see around the black hole is kind of an enhancement, so more light, because that's kind of light that gets bent from somewhere else, gets lensed by the black hole, and makes kind of this ring brighter. And actually what's also really interesting is you see one side that's brighter, so here this lower side is brighter than the upper one, which is because the black hole is rotating. So a part of the mass around the black hole is moving towards us, and the part is moving away from us, and the part that's moving towards us looks brighter because the photons kind of get extra energy from moving towards us. Actually, I'm not sure if the brightness is only because of lensing. I think it's also like the disk of the black hole that emits lots of radiation. Yeah, so this kind of a way you could kind of see a black hole if you call seeing the shadow seeing the black hole, because you can't actually look inside because there's just no photon, no light can escape out of it. So that doesn't really work. And we got a complicated looking question about lensing. Given the differences between the energies of different frequencies of light and the subsequent effect on field versus particle versus wave intuition, how does gravitational lensing affect different light frequencies? So let's say, what does lensing do to light of different frequencies?
So the frequencies the relative frequencies would be the same, but when we're lensing distant galaxies, we've got this other issue of redshift. So our biggest factor is we have to deal with redshift. So we have to account for redshift. So when we redshift with wavelengths of light, what we observe and what the galaxy originally emits will be two different wavelengths, because in the time it takes for the galaxy to emit that light and for that light to arrive us at our telescopes, it would take the stuff I look at is billions of years. It would take billions of light years for the light to get from the galaxy to us. So that's the thing we have to account for the most. But it's all relative. So when I was talking about magnifications earlier, everything will be magnified. So we just, at the end, we calculate our magnification by doing our very complicated lens modeling. So this is where we take our ring and we turn it from a ring and we trace it back and try to find what that position and the distances of these background sources or background galaxies are. So you just basically, you get a magnification factor and you just divide everything through by this magnification factor. It will have the same effect basically to everything. Everything will be magnified for the same amount.
Yeah, that's relatively nice of the universe to not mess up our wavelengths.
Yes, thank you.
We got we got one question about the Hubble law. So maybe let's explain a bit. Let me first start by saying what this is. So we observe that the universe is expanding, right? So when we look at galaxies that are far out, we notice they are expanding away from us. And the further out a galaxy is, the faster it's moving away from us. And the reason for that is the universe is just expanding. Like the whole universe, space-time itself is expanding since the Big Bang. And this is what we can observe when we look at galaxies. And the question is, this Hubble law, so the original Hubble law found by, I think, Hubble himself, is that the speed that a galaxy is moving away from us is proportional to the distance. So if a galaxy is twice as far away from us, it's moving away from us twice as fast. And this law is only valid for relatively short distances, because the further away you get, the situation gets more complicated, because the expansion rate of the universe is not actually constant. So the Hubble constant is only a constant in space. So it's the same everywhere, but it's not the same at all times. So in the early universe, it was expanding much faster than today. Well, actually it's accelerating again, but yeah, it's complicated. And if you look at nearby objects, the light is from, I don't know, a few years ago or a few thousand years ago, the Hubble constant didn't change that much. But if you look at objects that are billions of light years ago away, the light is billions of years old and the Hubble constant was very different. So you have to take that into account. And this is another thing, that galaxies are not only moving due to expansion of space, but they could also be moving towards us because, let's say, we are attracting them. For example, the Andromeda galaxy and Milky Way are on a collision course. So even though it's away from us, it's not expanding because it's also kind of attracted. And you have to look into this, because if you want to measure the Hubble law and you take a lot of galaxies and measure the velocities, you have to take into account, oh, they might be moving on their own and not only just from the expansion of space. So yeah, for a very nearby galaxy, you can't use the Hubble law at all because they are just moving on their own, and that's larger than the velocity they have due to the expansion of the space. And for really far out ones, you have to be a bit more careful and use the correct formulas to get the right velocities. Yeah, I'm actually having trouble to read all the questions. There's so many, but that's great.
Oh dear. That's good. No, it's really good to see.
So, if we had multiple galaxies behind our lens galaxy, what would this image look like? So if you have, yeah, right, so I guess
this
you
is kind of
could have two galaxies right behind each other or next to each other, right?
They'd have to be very close together. So I think fairly recently, and I don't know if this is published or not, but we come across what potentially could be merging galaxies. So these two galaxies that kind of come together and they're just like in the process of becoming one massive galaxy. And you would actually see two of these. So you'd have multiple images of maybe, so you'd have potentially two images of one galaxy and two images of the other galaxy, but they have to be very, very, very close. They're in the process of merging. So it can happen. It's just very rare. So gravitational lensing in itself is quite rare, especially when we get these nice single lenses. So these lovely Einstein rings is quite rare. So to get that would be even rarer, but it is doable because we have seen it. So yeah, you get multiple images of the different galaxies.
Yeah, actually, when two galaxies would be behind each other, would you also see them in the lens, or like where does a galaxy have to be? Does it have to be at a specific point to be visible as a lens? So let's say we have a big galaxy as a lens here, and we want to see a galaxy behind it. Does it have to be at a certain distance, or can it be anywhere?
I think distance-wise, it tends to be quite distant, but I don't think it has to be very specific distance. It's more in the orientation. So that's the position of the background. I'm just going to use my hands again. This position of the lens and the background galaxy. So if it's, like I said earlier, if it's directly behind our lens, then we're going to get our lovely Einstein ring. But if it's maybe slightly off, like out here, then you could get maybe one or two sort of images rather than the ring. We'll just get like arcs. And you can probably see this in clusters. If you look at the Hubble Deep Field, for example, if you look closely enough, so you have your galaxies, but you can also pick out some faint kind of blue arcs, and these are other galaxies that are being lensed. But yeah, I think it's more orientation than distance. But if you had two galaxies directly behind each other, then I think you'd get the lensing of the nearer galaxy, but I'm not entirely sure.
Okay. We also got a question from Periscope this time. At what distance should the sun be placed so we can look at it safely without any protection? Oh, that's a good question. I'm not sure. So, I mean, obviously there's a kind of a thing about how, like, if you move it a bit further away, you could look at it for a few seconds, but it's probably not too healthy. And the further away it is, the less dangerous.
Don't look at the sun.
Don't do it, okay. Yeah, well, I mean, if you can move the sun, sure, but as long as you can't move it, don't look at it. I mean, yeah. So
I mean, a safe distance would be like something that we see stars in the night sky, and that's not dangerous for us to look at those. So the nearest star is about how 4 light years away?
Yeah, right.
40 light years. So you could put it there and it not be dangerous, and you can still observe it. But I think you could move it like closer.
I mean, I suppose you could probably also. I mean, I'm sure 0.1 light years would be fine as well, but I don't know the exact distance. And I mean, I don't want to say anything about safety and health and safety here on the stream. So I'm not confident.
Don't look at the sun.
I'm not qualified to do that, and don't look at the sun. Yeah. Do you want to say a bit about how we can find out how old the star is, and maybe when it will go supernovae, especially Betelgeuse?
Okay, so everyone's heard of Betelgeuse, and it's been doing this strange thing recently. So Betelgeuse is in the constellation of Orion. It's one of the shoulders of Orion, I think. And Betelgeuse has been what we call variable, so it starts to get really dim. The light's gotten really dim, and it gets really bright, and it gets really dim. And about the end of last year, it went dim for a very long time, which suggested it could potentially be going supernova. And then I think about around Christmas, January time, just when we thought that Betelgeuse might go up, because if it goes off, we'll be able to see it for a couple of days in the night sky, and that'd be really cool. It'd be about as bright as Venus is, I think. So everyone was like, fingers crossed it will go up. And then it started getting bright again, which just meant it went through a patch of it just wants to be really dim for a while, and then went really bright, and it's fine. It's just being variable. How do we age stars? You can, I mean, colors. The colors of stars are quite useful, right?
I think so. Yeah. Let me pull up a HR diagram. There we go. Yeah. Right. So as long as the star is on the main sequence, I'm not sure how well. So okay. So let me maybe explain a bit about how stars kind of evolve. So we always look at this kind of diagram where we want to look at stars or discuss the evolution of stars, and it has here the kind of color on the one axis and how bright it is on the other. So here are red dim stars, and up here are bright blue stars, and here are bright red stars, and here are dim blue stars. And what happens with stars usually is they kind of form in some way, and they form somewhere, I don't know, around this edge here, but like after quite a short time, they land on this kind of main axis here, and they go from here, they go kind of to the right, up here, and then they do like a big turn around, and at the end, they end up down here at the white dwarfs. And for example, one thing that stars do when they stop burning, so stars always burn something, but they burn different things at different places. So a normal star in the beginning just burns hydrogen in its core. So in its core, it's fusing hydrogen to helium. We call this just burning usually. And at the shell around it is still full of hydrogen, but it's not getting burned. Well, it's not kind of getting fused. And eventually, all the kind of hydrogen in the core will have burned up, and then it will start burning hydrogen kind of around the core and the shell. Eventually, it will start burning helium, and it will go through different phases. And during those phases, star moves in this plot. So at first, when it starts burning, I think it's burning hydrogen in the shell, it moves up into this kind of giant branch, becomes much bigger and much redder, and then it moves around, like it eventually goes back kind of horizontally to the main branch, and it moves again. And if we look at the star and can kind of find where it is in this plot, we can kind of deduce the age more or less. I'm not sure how accurate we can go with this though.
I think we tend to look at what we call stellar clusters. So these are just groups of stars that are sort of formed at the same time. And we look at the colours that they're in those stellar clusters. So in the different, you can measure the age of them by looking at what the colours are. So if you have, say, blue stars still in the cluster, if it's quite a blue cluster, then it's quite a young cluster, because these stars, these bigger, bluer stars, they use up all their hydrogen much faster than, say, if you're further down. So these are much bigger, so they need to burn a lot more hydrogen, so they don't live very long. They use up all their hydrogen and energy and go off the main sequence. But if you've got stars, say, like our sun, and smaller stars, redder stars, then these tend to live a lot longer because these are a lot smaller and don't have to burn up as much. So all stars are born with like a limited amount of hydrogen. So if we can look at the colours, and if we look at the colours, then we can relate it to a time, and we can see how old our stellar clusters are and how old those stars tend to be. There might be some variation in the ages, but they tend to all be the same age, give or take.
Right. So we got a few more questions. I'm quite busy writing down questions here. So there's one question about why some stars just cool down, or I suppose like when stars cool down and why some cool down earlier than others.
Is this? I mean, in terms of like actually cooling, only white dwarfs cool if we're thinking about just cooling down. So in the sense that stars like our sun, they won't go supernova. Instead, what they do is they go up into this red giant phase, and then eventually they'll get rid of all their outer layers of their atmosphere and cool down into what we call a white dwarf. So these are very faint objects, but they also are not fusing anything. So they eventually would just cool. All their sort of energy just goes away, and by heat. But the times for these white dwarfs to cool down into something called a black dwarf would be long. It's actually longer than the age of the universe. So we haven't observed any of these black dwarfs yet. But if we're talking about in ages and lifetimes, then your blue stars, your big giant stars, tend to have shorter lives because they're much bigger and they need more fuel to keep them going, and they only have a finite amount of fuel, so they'll use it up quicker and then go off the main sequence.
I mean, of course, there's like kind of small variation to the temperature. For example, when a star goes kind of the red giant branch, it depends on if what we see of the star is if its surface is hot or cold. So that's actually the reason why kind of a white dwarf looks hotter than a kind of red giant star, just because we see its core, which is really hot, instead of its shell, which is kind of colder. So that's kind of the reason why they changed their color, I suppose. You got one question on how the Milky Way compares to other spiral galaxies in kind of our same class or the same size of galaxies.
I think the Milky Way is pretty standard.
Yeah, I think so as well. So there are different, like there are kind of types of galaxies with like bars in the middle, or with no bar in the middle. Like the structure can be a bit different, but I think the Milky Way is pretty average, yeah. Which is, I suppose, it's nice, so we can study it. It's not nice when you live in a really special place, because then it's really hard to study the average case. So that's nice about the Milky Way. We got a question from Slido again. So Rory's dad would like to know, why does the starry night sky look as if the distance away as the distance away as a daytime blue sky? Right. So kind of when you look up at the sky, how far does it seem away? I think it's, I'm not sure if you can, like, I don't know. I don't really see if the sky is at a certain distance away, because it's just like everything so small you can't, at least I can't really see any distance because there's nothing to compare to or so. So when you look in the day sky, you just see like a blue wall, and if you look at the night sky, well, you see kind of a black thing with a few dots sprinkled inside. But you can't, like, if you would want to see the size, you would need to see some extended object, like, I don't know, a ruler, an airplane. I mean, if you see an airplane, you can kind of figure out how far it is away, or with the moon maybe. But otherwise, it's really hard to see kind of the sky itself, because it's, I mean, the sky itself isn't even a thing, right? It's just it just goes on forever. It just starts with our atmosphere and then goes on all the way to the, I guess, edge of the opposite of the universe. Although, of course, we can't see that far. Yeah. Oh, there's a question for you. What things have been discovered by gravitational lensing till today?
What things
have been discovered by gravitational lensing till today?
So what things have we discovered? I think it's not really we've discovered new things with gravitational lensing. I think it's given us a way of studying things that we couldn't normally study. So these fainter galaxies, these more distant galaxies, and we can study these in more detail. So whereas we'd say maybe see a blob, really faint, like blue dot potentially, we can now see, like in the ring, in the Einstein ring we looked at earlier, you can pick out features of the galaxy. So you could be able to observe how the dust and the gas in the galaxy is moving, because the dust and the gas is really important for star formation. So the gas is what we need for stars, and then stars produce a lot of dust. Not say the dust we find here on Earth, but this is kind of like space dust, and you can tell a lot if you just look at the dust and gas content of galaxies about what these galaxies are doing. And there's this bit sort of this ongoing debate on how much the central supermassive black hole influences the galaxy it's in. So could it be stopping star formation by heating up the gas so much that it just completely stops star formation, and what's going on, and we can kind of get an idea of how these galaxies are evolving at these distances. Because when we talk about these far distances, we're actually talking about the universe was a lot younger than in those times. So it's kind of understanding what was happening in those times as well as like compared to what's happening now, because we know in the distant universe galaxies were forming a lot more stars. So nowadays, say with the Milky Way only forms about one, like what we call a solar mass, so mass like the sun, star a year. Whereas in these galaxies, the galaxies that I study, they tend to be forming stars of maybe 100 solar masses or even like 1,000 solar masses. And again, by using gravitational lensing, we're seeing more normal galaxies, so we can actually get an idea of what is actually happening rather than just seeing these bright objects, where these things are producing quite a lot and they're these extreme objects. So gravitational lensing hasn't found anything new, but it's a useful tool into like kind of looking at what's going on in the universe. Yeah,
actually, like kind of looking out in the universe, we got a few people who want to colonize other planets. So we got to question how we can get to other planets. And directly the follow-up question, is faster than light speed travel possible? Because I think those are two very combined questions. Well, how can we get there? Just fly there, I suppose. So build a rocket and fly to another planet. I suppose it doesn't really work for anything outside of the solar system. So I think we have no idea, well, we have no like reasonable way to travel to anything outside the solar system at the moment. And it's really hard to do. And kind of the main reason why it's hard to do is you have to carry all the fuel to accelerate yourself with you. So if you want to go to, say, the moon, then you have to carry all the fuel that you need with you. And let's say you lift off at the ground, you have to lift the rocket, the people, the equipment, and all the fuel that's inside for the remaining part of the journey, lift it up as well. And if you want to land, say, on the moon or even on the other planet, you have to slow down because you don't want to crash into the planet, right? So you have to carry kind of a, don't you? Oh.
No, so I'm just thinking about you don't want to crash into the planet. That's not fun.
Right, so you have to carry the fuel with you to slow down again. I think this is really impressive when you look at kind of the SpaceX rocket landings. So they land a rocket and they fire the rocket to land, so you need to slow down. And this is the same if you want to land a spacecraft on another planet. On the moon is quite okay because the moon is really light, well, relatively speaking. So it's much easier, you need much less fuel to land on the moon than on an actual planet. So if you want to land on an Earth-sized planet, you need a ridiculous amount of kind of fuel with you. Especially if you don't know what you'll find. Like if you find an atmosphere, you can use that to break. But if you don't have an atmosphere, it's really hard. And yeah, speaking of getting there, if it's like Alpha Centauri is our nearest solar system or nearest star, and I think it has a planet. I think it has us. I think we're not.
I think it has a few planets.
Few planets. Oh, that's even better. But it's still 4 light years away. That means even if we could travel with the speed of light, and we are far from that, it would take 4 years to get there. So realistically, hundreds of thousands of years to get there. So of course we want to find a way to travel faster than the speed of light. I think in principle, I mean, it's with our kind of current idea of how we accelerate would be just get faster and faster. And if we use general relativity, I think even special relativity would tell us you would need infinite amounts of energy essentially to get to the speed of light. So we couldn't get over the speed of light. Of course, it's possible that in the future we will discover new theories, hopefully, and figure out how this works. Also, the same goes for sending signals. So if you want to send messages to other civilizations, with our current understanding of science, this only works at the speed of light. But, well, I mean, maybe we'll eventually find something different. We got another question about spiral galaxies and elliptical galaxies. And the question was, if a spiral galaxy, is it just the same as an elliptical galaxy plus a disk, or are they more different? I think elliptical galaxies are actually larger, right?
So elliptical galaxies tend to be larger than spiral galaxies. So they're not just where structurally they're quite different. So with a spiral galaxy, you've got everything rotating around the center of mass. They're all rotating together, and it's really nice and lovely. Whereas with a elliptical galaxy, the stars have a lot of random motion as well. So even though they're kind of orbiting around the center of mass, they're doing a lot of crazy things as well. And it's thought that maybe when you look at comparing like the colors and the stellar populations in these galaxies, so our spiral galaxies tend to have a lot of younger stellar populations, and our ellipticals tend to have a lot of older stellar populations and lots of old stars versus lots of new stars. We think that elliptical galaxies come from potentially when spirals merge together. So they're merging and they're creating all these like crazy orbits of the stars, and the motion's a bit crazy. And then these are just sort of aged along. So all the young stars have, died out, and we've just got these older stars left over. But when these things merge, then you will possibly see a burst of star formation before it cools off. So they're a little bit different movement speed-wise, and they're also different color-wise. But they're all galaxies at the end of the day. And it's kind of just an evolutionary track, I think. So yeah, spiral's much younger, elliptical's much older.
Okay, back to accelerating and let's say space science again. We have a question about if space stations will eventually kind of move out of their orbits because of air resistance. And indeed, that's a thing. So it's not really, well, I mean, you could call it air resistance, but it's more like space stuff. Like, I'm not sure actually how you call the stuff up there.
Space resistant.
But, well, there is enough dust, and there are some molecules out there that slow down. Well, I mean, there's a kind of very thin part of our atmosphere, let's call it like this. Yeah. That's slowing down the space station and other, actually satellites that orbit around the Earth, especially satellites in a low orbit. So satellites that go around the Earth really fast, they are much lower in the atmosphere, which means they have a lot more air resistance, which means they either live much longer, shorter, or need more fuel to kind of keep them in the orbit. And the ISS in particular has the same, let's say, issue, like it also slows down. And I think what they do is the so-called reboosting. So they kind of dock one of those rockets that they sent to the ISS and actually fire some kind of engines for a bit to speed the ISS up again to the speed it should be at. So to always keep it at the designed velocity. We got another question from Slido. What's the conflict between general relativity and quantum theory? And actually, there was a question that we had a few times submitted before, but I didn't get to answer it yet, I think. Okay, do you want to say something, or should I throw up black holes?
I can do this.
Okay.
I mean, this will be go for it.
Okay. So we have quantum theory, quantum mechanics, which tells us all about how small things behave. So it tells us miraculously well about electrodynamics, the strong nuclear force, the weak force. It tells us about how protons work, what quarks do, how protons collide, how tables work, how computers work, all these things, right? And we have general relativity, which tells us what does a really, really heavy object do. So what does a sun do? What does a black hole do? What does the whole universe do? And the problem is, what happens if you have something that's very heavy, so you need general relativity, and very small, so you need quantum theory, quantum mechanics. And we don't really have a theory that kind of combines the two. So if you apply quantum mechanics, you can do a bit about like quantum mechanics and curved spacetime. That's how you get the Hawking radiation. But we don't have a theory that kind of really captures all of the effects in one. So if you have things like what happens inside a black hole, like what happens, there might be some kind of singularity. We have no idea because we don't have a theory for that. I mean, we also couldn't find out because nothing comes out of a black hole. But yeah, so the conflict between those theories, we don't have a single theory to describe heavy, small objects. In one sentence. What's the difference between a supergiant and a white dwarf? Well, I suppose are two very different things. Do you want to say a bit about this? Or should I?
The supergiant. I mean, it's up to you. The supergiants. I mean, these are much bigger. These are still somewhat fusing in their cores, but they have lots of layers of kind of leftover material where it doesn't fuse. Whereas white dwarfs. So these supergiants tend to be quite big. Whereas white dwarfs, they're not fusing at all, they're just cooling, and they're very, very tiny. These just tend to be the cores left over from these stars, whereas the supergiant still contains a lot of the atmosphere.
Okay, we got a few questions here on Slido that we had earlier in the live stream. So we discussed a bit about what's the difference between space rocks, aka asteroids, and planets. I think the short version was planets have to fulfill a few criteria. They have to orbit the sun, clear their orbit, so they have to like get rid of all the stuff that's also in their orbit and kind of claim this for themselves, and be round from their own gravity. And that's, well, everything that doesn't do that is not a planet, which also sadly kicked out Pluto. And if you want to find black holes, that's actually a nice thing. So you can usually find black holes at the center of galaxies. So if you go to the center of the Milky Way, you'll find a really massive black hole, a so-called supermassive black hole. And I think, at least as far as I know, the center of every galaxy there's a supermassive black hole. So
it's not like officially confirmed, but yeah, it's basically common. It's just accepted now that in the center of every galaxy there will be the supermassive black hole, whether they're active or not. So thankfully, our galaxy black hole's not active.
Right. That's also a thing with active black holes. So well, I mean, there's a black hole in every galaxy center, and it's in more massive black holes. It's usually much more massive. So this one in M87 is is it a billion or a trillion? I think it's a billion solar masses.
Billion sounds.
Well, yeah, anyway, it's 1,000. It's 1,000 times more heavy than the one in our Milky Way. So that's a big difference in sizes. But yeah, there you can find them. Also, when big stars explode, they leave behind a small black hole, so about a bit over 1 solar mass, essentially just whatever. Actually, I'm not sure about the exact size, but order of a solar mass, which is left over when the star explodes. So we are back to the aliens. Best way to find aliens? That's good question.
Interesting.
I mean, the one thing people are always trying is use, let's say, radio telescopes to listen for aliens. But that's a really kind of self-centric view of the whole thing, because the only way we're using radio waves to listen is because A, they kind of get through our atmosphere nicely, so we can actually listen to them, and B, because that's the technology we have. You could imagine, I mean, humanity existed for, 20,000 years, and in the last, 100 to 100 or so, we had radio waves. And I don't know, it will probably exist for a long time more. Like, I mean, our sun is going to live for a few billion years. So we'll probably develop much, much more advanced technology. And like expecting that aliens will like send on radio waves is, maybe they won't. I doubt it, especially if you think, if there is a way to communicate faster than the speed of light, then aliens will definitely be using that one. So if they do that, we will have no idea how to detect it at the moment.
I mean, we could look at exoplanets. I mean, even closer than exoplanets, we can look at potentially life in our solar system. So we're not talking like little green men, we're talking maybe like bacteria or microbes. And I think in some of the moons of Jupiter and Saturn, so these icy worlds, there potentially could be like water underneath them, and this water is being heated. It's kind of like ice volcanoes, and we think there might be microbes or bacteria, such as what we call extremophiles, because they live in the most extreme places where you wouldn't think life exists, and they do that on Earth. So potentially there could be life there, or looking for potentially biosignatures or signs of water on other planets, which we're just getting the ability to do. So that'd be really cool. But again, you know, I think it's going to be years, thousands, but hundreds of years at least, I think, before we find the little green men that we're looking for.
Ah, yeah, right.
Definitely bacterial and microbe. I'm fingers crossed for our lifetimes.
Hey, let's hope so. Speaking of this, we got a question: how many exoplanets did we already discover? I think it's around 4,000 now, actually. So there's I think most of them come from the missions. What was it? Kepler and TESS, I think, were the missions that discovered a lot of planets, and they're not all confirmed, but I think like 3,000-ish are confirmed, and 4,000, like 1,000 more are kind of being confirmed. And yeah, that's like a lot of planets. And actually, I forgot again. I think it's a normal case that stars have planets around them. So it's not an exception that we have planets, but it's usually kind of a normal case to have planets. I think the average number of planets is also quite high, but I'm not sure about what that number was. But yeah, there are tons of planets out there, like billions of planets, and we already discovered 4,000 of them. We were talking about active galactic nuclei or quasars before. Do you want to say a bit about what they are and if there are any nearby, or if they're all at high redshift? Or should I say it? Yeah, you go.
I'm happy to talk about them. So, active galactic nuclei. So, this is referring to the black hole at the center of these supermassive black holes. These supermassive black holes at the center of these galaxies. So when we say that AGN, active galactic nuclei, this means these galaxies are active, so they're actively feeding, they're pulling in material. So material kind of orbits around the black hole in what we call an accretion disk, and eventually this material will fall into the black hole, be pulled into the black hole. But as it does, it gets heated up, and with friction, so all this material is like rubbing against each other, and you'll get this light. It produces a lot of light, and we can observe this light, and a lot of the times this light outshines that of the light of the galaxy. So it's interesting, but when you want to study the galaxy in particular and explore how the black hole and the galaxy are related to each other, it's quite difficult. And again, that's where gravitational lensing can be quite useful, because if you're lucky enough to have alignment, so maybe the active galaxy directly behind the lens, then you could get your active galaxy as like 4 dots. So the black hole accretion disk is 4 dots, and then you could get the disk of the host galaxy into an Einstein ring, and that has been done, and that's really exciting, and that's kind of the goal of what I'm trying to do. So
let's hope you're successful then. That sounds nice.
So yeah, so we call them, they got many different names, and this just depends on what bit of the galaxy or the active galactic nuclei we're seeing. So sometimes we'll see the jets, like in this image, we'll see these massive jets, and maybe you'll have your galaxy in the center. Or again, if you're looking at like ideally we call them quasars, where we just see this, like, they look like stars because they're so bright, but they're not stars, they're galaxies.
Yeah, I just noticed I talked about redshift without explaining anything. When there's a phenomenon we call redshift or blue shift, depending on what direction it goes, and it's a similar thing to the Doppler effect that you have on Earth when you hear some sound. So when you have, let's say, like a siren that's driving away from you or that's going towards you, they have slightly different sounds. They sound slightly different. And the reason is when something is moving towards you and sends out light waves, you can imagine those oscillations that get kind of shorter because the source is moving with the kind of like behind, like a source is moving while emitting waves. And the same happens with astronomical objects. So when you have a star that's moving and then emitting light, this light gets stretched if it's moving away from us, and squashed, so it gets bluer when it's moving towards us. We usually talk only about redshift because essentially everything in the universe is moving away from us, except for like some really close things like Andromeda. So actually Andromeda would be blue shifted, or have blue shifted, let's call it this, or negative redshift, while all the other things are redder than they actually should be, so they're called redshifted. And yeah, right, we were talking about the black hole just a few minutes ago. That's a photograph of M87, and we got a really interesting, really good question. Why didn't we make a photograph of the black hole in our own Milky Way? Because that sounds like the obvious thing to do. there are 2 points to this. The one is it's hard to kind of see through all these stars in our Milky Way towards the black hole. So actually we can do that, and actually we did make a photograph of Sagittarius A star, so of the Milky Way in our of the black hole in our Milky Way. And also, you have the one problem of there's lots of stuff in the way, so you have to kind of look through this. And the other problem is that it's quite small. So as I said, the object there in M87 is 1,000 times larger than our Milky Way, so 1,000 times heavier. Also means the radius is 1,000 times larger. So the area is like a million times larger. So it's really much bigger, but also much further away. And this roughly cancels out, so they are roughly the same apparent size. And then it was the easier photograph to make. I think also the first one that was published was the M87 one, because we could kind of look head on and didn't have to look through all the stars that are just in front of our eyes. Was M87 bigger than our galaxy? Yeah, I'm not sure. Actually, I have it written down somewhere. M87 is quite a bit larger than our galaxy. I might have written it down somewhere, I'm not sure.
I think it's 1 trillion stars, whereas we've got a billion.
Oh yeah, right. So the galaxy is also 1,000 times bigger, just as a black hole. Yeah. So, do we have more questions? I've been reading not so thoroughly, so I might have skipped some. If I skipped your question, you might also just like send it again. Oh, actually, well, there's one question that I skip all the time, so maybe I should get to it now. We talked about the. Actually, okay, let me just quickly answer this question, and then we are already finished because it's 8 p.m. and we should stop at some point. Okay, we got another question. Okay, let me move the great detector question. I promise I'll answer it in the future. So if the person who sent this question, actually I think 2 weeks ago, come back next week and just tell me, and I'll explain the great detector. For now, we got one final question before we stop today. Can you tell us about some places in the universe where the possibilities of existing alien civilizations is huge? Example, many astronomers think that there can be alien civilizations in Brutus void. I would say that so with civilization you mean like actually intelligent life, like little green men or people like on Earth, I suppose. In general, for life existing, I would say it's just where the most planets are and the most stars. So where there are the most stars, there are the most planets, and more planets means more like opportunities for life to start. I think that what you're talking about is if there was life and we didn't detect it, where could it be then? Because if it would be nearby, okay, we might have detected it. But I don't think there's a special place, or do you know, Aoife?
I don't think so. I think it's just a case of where there's planets, there could be, where there's stars and there's multiple planets, your chances of finding life is higher. But yeah, I think it does exist somewhere, but we don't have the technology to find it yet. And I think the example was given when you're at Alpha Centauri, the nearest star to us, if you're on a planet around that star and you're looking back at Earth and you're looking like at us, we wouldn't be the humans we know today. We'd be monkeys. So we would still be monkeys.
Well, I mean, we would from Alpha Centauri would be 4 years, right?
4 light years.
Yeah.
That's true, actually.
But if you're like on another galaxy, like if you're on Andromeda, like if people would from Andromeda look at us, Andromeda, I have it written down here somewhere, is, what is this, 1 megaparsec? 0.7 megaparsec, which is roughly 2 or 3 light years away, million light years away. So they would see the Earth as it was 2 million years ago. So yeah, I guess they would.
That's the example.
Is it monkeys? I don't know what was 2 million years, but certainly no humans like we know them today. So yeah, that's kind of the idea. Like, I think there could be aliens in our galaxy and we wouldn't know because it's just too far away. Yeah. So if you have questions left over, just feel free to come back next time and send us the questions, or send us in advance some questions either here on Slido or on the website that's scrolling up in the top left corner once in a while. So thank you all for watching. Thanks for asking so many questions. That was really great. Thank you, Aoife, for answering so many questions and talking about all the things I have no idea of.
I really enjoyed it. So thank you for all the questions. It was really good. Good fun.
Yeah, you feel free to subscribe to our YouTube channel if you want to see some things. I think there are like lectures or like talks are being uploaded, some public outreach talks. Some live streams are made, I think, once a week, Tuesdays, if I remember correctly. Not sure what's up for tomorrow. But yeah, check there. Also, you can follow us on Twitter or the Astronomy account to get tweets when we go live again. But it will be every Monday for now at 6 p.m. British PST, 7 p.m. Central European Time, 5 p.m. Universal Time, 1 p.m. Eastern Time. That's all I can remember in my head. So thank you all. Thank you, Aoife, and see you next week.